But I'm here, you're here. Let's get going. Good morning, everybody. Welcome to another sunny, wonderful morning of Chem 1211 with your host, me, Dr. White. And today we're going to do a lab. But in order to do the lab, I've got to teach you something because today's lab is equilibrium. Really, it's about Le Chatelier's principle. By the way, that's my North Side Chicago French accent. I don't do well pronouncing French names like that. I've had two students who spoke fluent French. When I said that, they started laughing. I said, "What's the right way?" And they taught me. And I said, "Good. Now I'll still call it Le Chatelier." And they started laughing. But anyways, guess what? Oh no, you don't know about Le Chatelier's principle. So how can you do the lab? I've got to teach you. By the way, joke from yesterday. Near the end of yesterday's lab, I said, "Oh, you know what I can do today on Friday? I can replay the video from yesterday." So is this live or is this a video? It's live. I'm not going to cheat you. Look out, it's Wacky Friday. Nope, that's not what I want. That's what I want. All right, quick thumbs up, people. Do you see Le Chatelier's principle? Thank you. All right, today's lab deals with equilibrium and Le Chatelier's principle. Now, let me remind you, what is an equilibrium reaction? If you see on your screen now, I hope you all do, A plus B is in equilibrium with C plus D. What does this mean? The double-headed arrow tells you if you mix A and B together, it goes this way to make C and D. If you mix C and D together, they'll go this way to make A and B. This is an equilibrium. At equilibrium, as I taught you before, the forward and reverse rates are the same. And we talked about on Wednesday the equilibrium constant, which is a number based on the concentrations of the reactants and products. Now, the important thing to remember is at equilibrium, there's a certain amount of A, certain amount of B, certain amount of C, and a certain amount of D. Now, before we go further, there's some basic things I have to teach you that students have a hard time wrapping their head around, but I found a way to help students out. Now, let's assume you have a French silk pie. Dr. White loves French silk pies, even though I need one like a hole in my head, but I still love them. And if you have a whole pie, French silk, I like blueberry too. Apple, it's okay, but give me French silk, I'll be happy. But anyways, if you have a French silk pie and you eat half of it, you really pig out. Do you have the same amount of pie, more pie, or less pie? Trick question. And time's up. The answer is you have less. Less. Why? Because you consume some of it. Boy, did I consume some of it. But anyways, when you consume something, you have less. Now, let's assume you're making cookies and you don't have any cookies in your house and you're making some. Now, after you make the cookies, you produce cookies. Do you have the same amount of cookies when you start out, less or more? Assuming you don't eat any before you start counting. And the answer is more. When you produce something, the amount you have increases. You have more. So when you consume something, like the French silk pie, no, I'm not going to go out and buy one now. Bye. No. But anyways, that's true, Danny. And I sometimes can be the cookie monster, especially around Girl Scout cookie mint cookies. Those just evaporate. But anyways, back to chemistry. So if you consume something, you have less. If you produce or make something, you have more. And that's an important concept you need to remember. Now, let's get back to Le Chatelier's principle. Now, Le Chatelier's principle, if you're reading in a book, says when a chemical system at equilibrium is disturbed, the system shifts in the direction that minimizes the disturbance. Hold on, question. Got it. What does that mean? Well, let's look at another way of saying it. If a stress, which is otherwise known as a change of condition, is applied to a system in equilibrium, the system will readjust, change the position of the equilibrium in the direction that best reduces the stress imposed upon it. What? Oh, my head hurts. No, let's do this. First of all, so let's assume you're at a party and somebody's being obnoxious and talking to you and poking you. You're under stress. You're going to do something to remove the stress, like stop doing that. Well, Chattelier's principle doesn't do stop doing that, but it's the same thing. Let's look at how you apply it. Everybody see my whiteboard? Notice whiteboard on white on white. Never mind. All right, let's look at that same equilibrium. And I see a question or comment. Hold on. You're right, that was bad humor. Watch out. Bad humor is slipping out of Dr. White today. Make sure you have your bad humor protection on. All right. All right, let's look at the question. What happens to the concentration of B and A? Remember, this means when you put something, a molecule in the brackets, that's moles per liter concentration, molarity. So what happens to the concentration of B and D, meaning how much, if I add more A? Now, first of all, let me check. Everybody sees the whiteboard, right? Thank you. Now, at equilibrium, there's a certain amount of A, certain amount of B, certain amount of C, and a certain amount of D. And it equals the equilibrium constant in the formula I showed you. Now, if I add more A, all of a sudden, there's too much A. And the equilibrium says, oh no, we've got too much A. How do we get rid of this excess A? Well, there's only one way it can get rid of the excess A, and that is A plus B reacts to make C plus D. When anything reacts, it's consumed. When something is consumed, you have less. So if you want to get rid of the excess A, you react it with B. Therefore, if you react B with A, B is also consumed. So what happens to the concentration of B? It decreases. Remember, just like if you consume half of the pie, you have less. You consume some of the B. When it reacts with A, you have less. Now, when A reacts with B, what do you make? More C and D. When you make more something of something, in this case, C and D, the amount you have, the concentration increases. And that's the Chattelier's principle. The stress was I added more A. At equilibrium, there was a certain amount of A. Now there's too much A. And it goes, oh no, we've got too much A. What do? We've got to get rid of this excess A. Well, it reacts with B, it's consumed, and when it reacts A plus B, it makes more C and D. So when it reacts with B, B is consumed, there's less, the amount decreases, and when you make more C and D, the amount of D increases. Now, when this shifts like that, the final amounts will now equal the equilibrium constant. But that's the concept behind Le Chatelier's principle. And not to scare you, but I will, that's going on right now in your lungs. That's how your lungs help bring in oxygen and get rid of carbon dioxide. Le Chatelier's principle. Your blood, I'll teach you more about it, uses Le Chatelier's principle. Oh, this is getting scary. And I'm not sure, but I think either your liver or your kidneys, one of those two, uses Le Chatelier's principle. Really? Yep. And chemists like me use it all the time. Let's do another one. And the question is, what happens to the concentration of B and D if I remove some A? And we can do that in chemical reactions, either side, add or remove things. So at equilibrium, let me clean this up first. At equilibrium, there is a certain amount of A, certain amount of B, certain amount of C, certain amount of D. And it's shifting back and forth and everybody's happy. You didn't know molecules could be happy. They can. And now we take away some A. And the equilibrium says, oh no, we don't have enough A. Someone took A away from us. We need to make more A. So it will be an equilibrium. How does it make more A? C and D react to make more A and B. So C and D reacts. What happens to the concentration of D? If it reacts, it's consumed. And just like the pie, you eat half the pie, do you have more or less? You have less. So if you consume D by reacting C and D together to make more A and B, because you need to make more A, the concentration of D decreases. Goes down, which is a synonym. Oh, look out, he's using fancy words today. And if C and D react to make more A and B, well, you're making more B. How much, what happens when you make more of something? The amount increases. Or you could have put down other synonyms. Oh, he's using a fancy word again. Gets bigger, gets larger, is however you want. And that's Le Chatelier's principle. And let you try one. Why don't you try this one? What happens to the concentration of B and D if I add more C? And while you're doing that, I'm going to clean up this. Now, I should warn you, this is a little more complex than normal chemistry because you have to use, take a deep breath, logic. Take a deep breath. And I'm teaching you how to use, take a deep breath, logic. Organic chemists love logic because we use it a lot. Again, you're trying to find out what happens to B and D. Now, I'll give you a little secret. Guess what? The answer, it stays the same, is never, ever going to be correct. You got two choices, either increases or decreases. Let's try a poll today. I think some of you are still working, so I'll give you a little more time. Let's see who has their camera on so I can see your pretty faces. I'm going to have to convince some of you who don't have your camera on to try and turn it on because that makes Dr. White happy and more motivated. Don't you want me happy and more motivated? Everybody say yes. So turn on your webcam. All right, let's do this. Question is, what happens to the concentration of B and D if I add more C? At equilibrium, there was a certain amount of C, A, B, C, and D. Now I've added more A, and it's under stress. Oh no, we have too much C. We've got to get rid of it, and I'm under stress. So I'll use the Chatelier's principle and shift in the direction to get rid of the excess C. How do you get rid of excess C? C plus D react to make more A and B. Well, C reacts with D, D is consumed. And when anything is consumed, the amount you have is less or it decreases the concentration. Or if you're lazy, you can just put an arrow down. That's acceptable on a test too. Or you can say less. All those work. Now, C and D make more A and B to get rid of the excess C. So if I'm making more A and B, because the reaction is going this way, what happens when you make more of something? What happens when you can't write a B? Let's try that again. That's better. When you make more of something, the amount you have increases. There's an increase, and you can put it, or you can say you have more. And that's the Chatelier's principle. But wait, let's consider the following. Now, we did the effect of concentration changes on the equilibrium, with Chatelier's principle being applied. Seaboard, well, I've already done that. The effect of change in temperature on equilibrium, and that involves an exothermic reaction and also is true for endothermic reactions. Let me just remind you, exothermic reaction when you react, it gives off heat or energy. And for this class, the energy will be heat. An endothermic reaction is you have to add heat. So this is an exothermic reaction. Why? Because heat is on the right of the double arrows. By definition, chemists have made that exothermic. When heat is on the left, we call that an endothermic. You have to add heat. Now, before we go on, there's something I have to teach you. And that is time for Dr. White's artwork. And if you want to laugh your head off, feel free to. This is a hot plate. This is water in a beaker, and it's boiling. Now, when you put a reaction like in a test tube in water, what happens? When you put a test tube in boiling water reaction, you increase the heat. You add heat. Now, the opposite of that is an ice bath. And no, I'm not going to try and draw ice cubes. I think many of you would get injured laughing too hard, and I don't want that on my conscience. And an ice bath is a beaker of water with ice cubes in it, ice. And what does an ice bath do? It lowers the heat. In other words, it removes heat. So you should remember, boiling water adds heat. Ice bath removes heat. I'll say it again, instant replay. Boiling water adds heat. Ice bath removes heat. And if you think about it, if we're in the middle of winter and it was super cold outside and you went out in a short sleeve shirt or top and shorts on, oh no, I'm getting cold. Why? Because the cold temperature is removing heat from your body. And if you go outside and it's super hot, oh, am I hot? Why? Because the higher temperature around you is adding heat to you. So let's look how that affects Le Chatelier's principle. For an exothermic equilibrium, and it's abbreviated EQ, I'm lazy this morning, Why don't you try this one first? You have that exothermic reaction. A plus B is in equilibrium with C, D, and heat. What happens to the concentration of A and C if I add more B? Your turn. Remember, at equilibrium, there was a certain amount of A, B, C, D, and E. And now you've got too much B. Oh no, we have too much B. Now be quiet now, maybe. And when you're done, give me a thumbs up. And if you don't have your camera on, use the emoji. Actually, I don't like the word emoji. I'm going to come up with my new word. I'm going to call it symboli. Use the symboli. Some of you like that. I'm getting to Better Humor Friday. Don't forget to use your symboli. That sounds Italian. I even crack myself up sometime with good humor. All right, let's do it. At equilibrium, there was a certain amount of A, B, C, D, and heat. And now we've added more B, and the equilibrium says, oh no, we've got too much B. We've got to get rid of some of it. It's the stress on the equilibrium. So how does it get rid of excess B? A reacts with B to make more C and D. Well, if something reacts, it's consumed. And A is consumed, therefore, when something is consumed, the amount decreases. Goes down. Now, when you make more C and D, what happens to the amount of C? Well, when you make more of something, the amount you have increases. And that's how you do it. But now let's look at the following. For an exothermic reaction, what happens to A and C if I put the reaction in an ice bath? And Dr. White will do this one. And therefore, at equilibrium, there was a certain amount of A, B, C, D, and heat. Whoop, just wiped out A. Hold on, we'll get you back. There you are. At equilibrium, there's a certain amount of A, B, C, D, and heat. Now we put that in an ice bath, and what does an ice bath do? It removes heat. So the equilibrium says, oh no, we don't have the right amount of heat. Somebody removed it. We've got to make more heat. How can it make more heat? A and B react to make more heat. Well, if A and B react, A is consumed, and you'll have less. The amount decreases. goes down. Now, if to make more heat, you react A and B to make the heat, it also makes C and D. When you make more of something, excuse me, C, you have more, and the amount you have increases. Goes up, gets bigger. And that's how you use Le Chatelier's principle. Oh, let me let you try one. So you can see the what happens to the concentration of A and C if I put the reaction in boiling water, a beaker of boiling water. Remember, boiling water adds heat. Your turn. And when you're done, give me a thumbs up. Or if you don't have your webcam on, use the symboli. Otherwise known translated as emoji. I like symboli better. Everybody in your Twitter feed, start using the word symboli. All right, since nobody's using their symboli, I'm going to do this. Well, I think everybody's done. So let's continue. All right. Now the question is, what happens to the concentration of A and C if I put the reaction in boiling water? What does boiling water do? Adds heat. At equilibrium, there was a certain amount of heat, A, B, C, and D. And now we've added heat, and the equilibrium says, oh no, I've got too much heat. I don't know if they raise their hands and go like that, but we've got too much heat. We've got to get rid of this excess heat. How can it get rid of heat? It has to be consumed by reacting with C and D. And then the heat will be less because it's consumed. When you have heat and C and D reacting, it makes more A and B. Well, first of all, C, D, and heat are reacting. C is consumed. And just like the French silk pie, I'm going to have to get that out of my mind. But anyways, when you consume some of it, the amount you have will decrease. Go down. Now, when C, D, and heat react, they make more A and B. If you make more of something, the amount you have, the concentration in this case, will increase. And that's how you do exothermic reactions. So far, and I haven't done this, any questions so far? Looking at the chat thing. No, I'm not trying to show my head. All right, let's continue on. Haven't done it for a while. Let me check something. Yep, I'm still recording. Remember, keep an eye on your screen to make sure I haven't hit the pause button. They're right next to the share button. Stupid. All right, thumbs up, people. Do you see endothermic on your screen? Thank you. All right, this is an endothermic reaction. How do you know? You add heat. Heat is on the left. So let's take a look at the following. Your turn. What happens to the concentration of F and H if I remove some G? Your turn. I'm going to work you hard today. I already am. And when you're done, use the symbole or use the real life symbole, thumbs up. Well, I guess I've confused people. I better go back to use the emoji. Or I can do this. All right, looks like just about everybody's done. So, whoop, that's not what I wanted. Let's get to work. All right, at equilibrium. there was a certain amount of heat, certain amount of E, F, G, and H. If I remove some G, the equilibrium says, oh no, we don't have enough G. We've got to replace it. So we'll be happy at equilibrium. And therefore, how do we make more G? We react heat, E, and F, and that makes more G. If we make more G, we will make, for a second I thought I had backwards, but I didn't. We want to make more G, we also make more H. And if you make more of something, the amount you have increases, goes up. Now, if we react E, F, and heat, F is reacting, is consumed. That's what happens in a chemical reaction for a reactant. And therefore, remember, reactants are on the left, products on the right, the amount will decrease. Goes down. Now, your turn again. B, what happens to the concentration of F and H for this reaction if I put the reaction in an ice bath? Remember, an ice bath removes heat. And if we were in a classroom, I could see all you wonderful students working on your chemistry. I'd say, when you're done, look up and smile. I actually do that when I'm in a face-to-face classroom. I get to see everybody's smiling faces. But I said, if you don't want to, you can also frown, but please smile. Dr. White, this is dangerous in a classroom as he is on Zoom. All right, looks like everybody's done. Oh my goodness, I think you're getting the hang of it. Aren't you proud of yourself? By the way, I didn't want to scare you, but this is pretty high-level chemistry, and sometimes students have trouble getting it, but I think you are. All right, let's look at the question. What happens to the concentration of F and H if I put it in an ice bath, the reaction? Well, that removes heat. At equilibrium, and let me clean up this. at equilibrium, there was a certain amount of heat, certain amount of E, F, G, and H. When I put it in the ice bath, I remove heat. And the equilibrium goes, oh no, we don't have enough heat. Someone took it away from us. We've got to make more heat. That's the stress with Chattelier's principle. And it needs to make more heat. How does it make more heat? G and H react to make more heat. When something reacts, it's consumed, H is consumed, the amount you have will decrease, go down. Now, when you make something and we're making more heat, we also make more E and F. And when you make more of something, guess what happens? The amount will increase. And let's do one more. On a test, I won't tell you if it adds or removes heat. You've got to learn that. But let's look at the new A. Your turn. What happens to concentration of F and H for the endothermic equilibrium if I put the reaction in a beaker of boiling water? And when you're done, give me a thumbs up. Or not to discriminate against the other fingers on your hand. You can use any other finger too. I guess I could say, give me a thumbs up or a pinky up. Nah. All right, I think everybody's done. Let's do this. What happens to the concentration of F and H if I put the reaction in a beaker of boiling water? Now, what does boiling water do? Well, someone was nice enough to write down it adds heat. At equilibrium, there was a certain amount of heat, E, F, G, and H. Now, there's too much heat because somebody added heat. And now the equilibrium says, oh no, I've got too much heat. I've got to get rid of some of the excess heat. How does it get rid of the excess heat? Heat reacts with E and F to make more G and H. Well, if you react something, it's consumed. F, E, and H reacts, so F is consumed. And when you consume something, like eat half of the pie, the amount you have decreases. It goes down. Now, at the same time, to get rid of the excess heat, it reacts with E and F. What does it do? It makes more G and H. Therefore, if you make more of something, H, the amount you have will increase. And that's Le Chatelier's principle. The equilibrium shifts in the direction to remove the stress. And therefore, it reduces the stress and it comes back to equilibrium. And that's Le Chatelier's principle. And that's how your lungs work and other parts of your body work using that. Now, in the chemical industry, let me give you a quick thing. I've done reactions where you react two things together and you make a product plus water. And to drive the equilibrium this direction, you remove water. And there's a way of doing that in a chemical plant or in a laboratory. It's called vacuum distillation. And by removing water, you make the reaction shift to C and keep on making more C. And it works quite well. And what's amazing is in a chemical plant, and later in the semester, don't tell anybody, but I'll be taking you all on a trip to a chemical plant. That's a place where most people have never seen the inside of because you want to keep it a secret from your competitors. But Dr. White was able to get around that. So I will take it out of the video though, to protect the innocent now. But anyways, I've done it where in a chemical reaction, we remove about 5,000 gallons of water. Now, what's 5,000 gallons of water? How many of you have ever seen a truck that delivers gasoline to a gas station? Raise your hand. I think you all have. Or sometimes you'll see it with milk in it. Not going to a gas station, though, I hope not. But anyways, those are called tank wagons. Those are standardized. 40,000 pounds, 5,000 gallons. So when we do a reaction, we take off enough water to fill a whole one of those up. And it helps make the reaction go to completeness and finishes it off. Otherwise, with the equilibrium, if we didn't do that, we'd be sitting around for days and days and days and nothing would happen. So chemists use Le Chatelier's principle, and your body uses Le Chatelier's, not only mine, but yours. All right. Oh, I look at the clock. Time flies when we're having fun. I went a little over today. We're going to take a 5-minute break and we'll come back and finish the lab. I'll get you out early. I promise I'll get you out before midnight. And with that, I'm going to take a 5-minute stretch break. I'll see you in 5. Come back at 10 o'clock. That's when the big hand is on to 12. Time to get going. All right, thumbs up, people. Hold on, I got the wrong thing, so don't thumb up yet. Everybody see Lab 11 on their screen? Thank you. All right, let's talk about Lab 11, equilibrium reactions and Le Chatelier's principle. Oh no, I'm still using my North Side Chicago French accent. Now, as I told you, in equilibrium, you have a forward and reverse reaction. And you can have two types of equilibrium besides this one here. You can have an exothermic reaction where you have heat also being given off, or an endothermic where heat is added, as I have here. Now, talked about Le Chatelier's principle. If a stress, a change in condition is applied to a system in equilibrium, the system will adjust, change the position of equilibrium in a direction that best reduces the stress imposed on it. And these changes in condition can include adding or removing reactants or products, or adding or removing heat. And as I've just mentioned earlier today, if you put a reaction in boiling water, you are adding heat. If you put it in ice water, an ice bath, you remove heat. Now, in this lab, you'll be examining the effects of adding reactants and products on equilibrium, and also examining the effect of adding and removing heat on the equilibrium. When you do this, you'll be able to determine if the equilibrium reaction is exothermic or endothermic. And what I mean by that is you'll be given two reactions. Now, just for discussion, and you'll, based on the labs you'll do today, you'll determine, does heat go here or does heat go here, plus heat? So at the end of each equilibrium, you'll be able to write, if it's an exothermic, the actual equilibrium is this. What I'll give you is this, and you'll determine heat goes on there. If it's exothermic, if it's endothermic, then heat would go on this side, and you write this equation. And that's the important thing. You have to determine and write the equation which side heat goes. Good news, we're not going to use letters of the alphabet. We're going to use real chemicals. And Dr. White's sad again, because it's so much fun to watch you guys do this lab face to face. But one of them, I have a YouTube. Now, in part one, you'll be looking at cobalt ions equilibrium. Here is the equilibrium, if I show it to you. Everybody see cobalt on the screen? Thank you. All right, cobalt tetrachloride anion reacts with water in an equilibrium to give cobalt hexahydrate and chloride anions. Now on this side, if this is shifted to the left, you'll see blue. If it's shifted to the right, you'll see pink. And you'll be using Le Chatelier's principle to determine if this is an exothermic or endothermic. So does heat go on this side or does it go on this side? You're going to have to find that out. How do we do that? By adding things. In the first part, you'll put the solution in a test tube. Then you'll record the color of that. I've done that already for you, but if you were in real life, you'd be doing this. Then you add 5 drops of DI water. GI stands for deionized, no other ions, water. And what that does is increase the concentration of water. And if I'm telling you the truth, it should turn pink. Dr. White might be lying to you. No, he's not. Then you're going to add some HCl. In water, we'll learn in the next chapter, this dissociates to H plus Cl minus. So by adding 5 drops of 12 capital M molar HCl, it's very concentrated HCl, you're really adding Cl minus. And when you add the HCl, if you add Cl minus, it should shift to this way and go blue. Now, what you have to do also is you put that test tube in boiling water and look what color it is. And then afterward, you take it out and put it in an ice bath and look what color it is. Then you put the stuff in a proper waste bottle because you don't want to throw this down the sink. And here I have the data when you do those things. Everybody see YouTube on your screen? Thank you. All right, if you notice, they're doing the same equilibrium we have, the same reaction, and they already have this equilibrium in these 6 test tubes. And now they're adding water to test tube 2. And notice it's still sort of pink color or chartreuse. It starts out, but it's now more pink. Now they're adding Cl minus. Oh, look, it's going blue. Is that wicked? Isn't chemistry great? Dr. White's having a good time now. I love Le Chatelier's principle. Now look at, you're putting the equilibrium in hot water and in an ice bath. And the hot water is turning blue. In the cold water, it's pink. And that's neat. Now, if you look on Blackboard, Dr. White did something nice for you. There's a equilibrium help sheet. And let's look at that help sheet. And notice the everybody see the help sheet? And when you add water, you increase the H2O. When you add HCl, you put in more Cl minus, and you saw it shifted when you add the HCl, it became blue.
Okay, in this video, we're going to look at an important part of chemistry called Le Chatelier's principle. And this is all about reversible reaction.
Sorry about that. I always forget to turn off YouTube and it goes on to a new YouTube. I hate that. I know how to shut it off, but I usually forget to do that. Let's get back to where we were. Now, when you put it in the boiling water, it adds heat. You got to look what color it is. And when you put it in ice bath, it looks what color it is. Now, here's something. When you put it in an ice bath, you're removing heat. Therefore, the equilibrium will shift to the side with heat. When you're putting it in boiling water, the equilibrium will shift to the side without heat. And that will help you determine which side has the heat and which doesn't, based on the color. If it's blue, it's shifted to this side. If it's pink, it's shifted to this side. And that's how you do part one. Now, let's look at part two. And notice I have the colors there. Now in part two, everybody see part two on your screen right now? Thank you. We're looking at the equilibrium, a solution that has ammonium chloride, NH4. Now that's a solid in water. It's an equilibrium with ammonium cation, the chloride anion, which are in solution. So this side on the left has a solid. On the right is clear. And you'll be using the Chatelier's principle to figure out which side, right or left, does the heat go. Now, first of all, you'll put the mixture in a test tube and look at whether it's clear or there's solid in there. Then, like I said in part two, you'll add 5 drops of 12 molar HCl, which adds chlorine, anion. That means when you add it, it should go solid, or you see a solid in there, otherwise known as a precipitate. And then afterward, you'll put it in boiling water and look and see is there a solid present or not. And then after that, you'll put it in a beaker of ice water and then look and see is there solid or not. And here I give you the data. And HCl, when you add it, a solid is present, which is expected. It would shift it this way. By adding HCl, we're adding more chloride, and we'll shift it and see the solid. Now I have the other things that I have here. When you put it in boiling water, it's clear. When you put it in an ice bath, there's a solid present. And don't tell anybody I'm being nice, but I also put part two in the help sheet. And when you add HCl, hydrochloric acid, you increase the chloride anion. When you put it in water, boiling water, it adds heat. When you put it in an ice bath, you remove heat. And what I have up here also applies. Boiling water shifts the equilibrium to the side without heat. Ice bath, you remove heat, same thing down here, you shift the equilibrium to the side with heat. And that will help you determine which side has heat and which doesn't. And yes, there are questions. And if you notice, I have different questions, and I have that phrase that students hate, explain. Now, in number 3, you're asked to write the equation for part 1, which is up here, and then include heat on either the right or left. Either it will say plus heat on the left or plus heat on the right. And that's the answer you have to figure out based on your data and what you learned today. And the same thing in part 2, I asked you some questions, and I used that ugly word students hate, explain. And then for number 6, write the equation for part 2. Please include heat on one of the sides. And that's today's lab. And good news, we're done. And I get to say, have a great weekend. I hope your weekend is better than mine, because I'm going to be grading tests and labs. But you're worth it. And my other class too. I gave them both, you and them, a test. So today, tomorrow, and part of Sunday, I'll be grading labs and tests. Plus, I'll have to vacuum and clean my bathroom. Yeah. But anyways, I'll teach you later in the semester how to clean your bathtub real easy. So it's not that bad. But anyways, with that, I get to say, have a great weekend. Gang gesund. Goodbye.